All right. Hi, everyone. We'll go ahead and get started. So I'm really pleased to introduce Dr. James Thompson from the BEG. James and I started, I think, the same year. Yeah, and even though we have some overlapping research interests, we still haven't been able to really meet and learn about each other's research. So this is really exciting for me. So thanks for being here. So yeah, James is a research assistant professor at BEG. He received his PhD in geology and environmental science from the University of Pittsburgh, and there he was also a NASA predoctoral fellow. And before that, he received his master's in volcanology from the University of Bristol and his bachelor's in geology from the University of Southampton. So before coming here, he was also a postdoc at Baylor University and University of Pittsburgh. So James focuses on developing novel remote sensing and geospatial techniques to understand the thermodynamics of terrestrial processes and determine the consequent societal impacts. He applies a multi-instrument approach utilizing a variety of data types to evaluate different surface characteristics and apply these to geological modeling applications. He's also leading an effort developing miniature thermal infrared imaging systems for deployment on unmanned aircraft systems to improve understanding of wildfire behavior in Texas. And this allows the derivation of critical gas flux rates in 3D, helping to identify wildfire burn efficiencies and the impacts of wildfires on ecosystems and air quality. James is also part of a team developing thermal anomaly detection and surface mineralogy algorithms. Still not really sure what that means. Hoping to learn today for the upcoming NASA Surface Biology and Geology satellite mission. And lastly, James is co-leading the Earth Hazards strategic investment at the Jackson School with UCO. So thank you for doing that too, James. All right, so looking forward to your talk. Thanks for being here.
Cool. Oh, great. Yeah, thank you for that lovely introduction, and thanks for sharing your morning with me, everyone. So yeah, I'm gonna talk to you about how I use infrared remote sensing from a variety of scales to understand geohazards, or more specifically, volcanoes and wildfires. Stuff I'm going to share is long collaborations with the University of Pittsburgh, Baylor, Northern Arizona University, as well as partners, the U.S. Fish and Wildlife Service, NASA, and through the FireSense project as well at NASA. So just want to mention those. I'll start out today giving you a quick outline. I'll try and prove to you why thermal infrared spectroscopy is a great tool to use for a variety of different Earth hazard and Earth processes to better inform them and give us a better understanding of the interplays and feedbacks of those and how they relate to humans and across scales, from looking at micro scale laboratory experiments all the way up to system wide landscape processes. So I'll start off by sharing with you some work I've been doing in volcanic hazard modeling. This is specifically looking at thermodynamics of lava flows and modeling of those lava flows. And we use high spatial resolution spectral images to understand those dynamics in near real time and across time scales. And then finally, in the second half of the talk, I'll go over some of my wildland fire science work that we've been doing, looking at all kind of main stages of the fire life cycle, from pre to active, post, and then also touch into air quality as well. And so I mostly do wildfire science on local scales, looking at single burn units or single burns, not really looking at the larger scale kind of system-wide processes, but very interested to talk with you if you have interest in using what I do and extending that beyond the regime that I'm mostly investigating right now. So mostly, as Danielle said, looking at fire behavior using infrared spectrometers, and then go over the role that fire has on ecosystems, both vegetation and soil dynamics post-fire, and then I'll finally touch on some air quality in urban regions and how that work is progressing. So why infrared spectroscopy? This slide's just a tidbit of some of the applications it has for earth science, from anywhere from looking at coral reef, coral reef distribution and health, looking at mineral mapping for critical minerals, methane emissions from processes that we use for energy sector, etc. Looking at vegetation health, crop science, volcanology, which I'll talk about a lot today, and then also something that I'm also interested in wildfires. This is just a small plethora of the way we can use infrared spectroscopy, but hopefully you'll find a use for it in the future if you don't already. So why do I use infrared spectroscopy? It's a non-destructive technique. You don't have to have physical contact with the surface, whether that's a solid, liquid, a gas. And it helps us it measures the infrared radiation emitted by a material. And it can give us two things. It can give us a composition or its state, and also the temperature. Particularly how you look in the thermal infrared region of the infrared spectrum. If you look at this bottom figure, where's the pointer? Down here, this is an EM spectrum all the way from gamma rays all the way along to long radio waves. I work mostly in infrared and visible light, but particularly in thermal infrared. The terminology changes depending on who you talk to, but mostly long wave radiation to long wave infrared or far infrared. But the wavelengths are the most important thing here, so 7 to 50 microns. But for Earth applications, because of the atmosphere and the atmosphere attenuating our signal, we mostly concentrate in the 8 to kind of 15 or 14 micron region for Earth applications. So we don't have to do so many corrections for kind of interference and improve our signal to noise of what we're measuring. Infrared spectroscopy is bound by first order principles, Planck's law being the main principle here. So the emission intensity or radiance, as it's referred to, depends on temperature and wavelength. And so here I've just modeled or calculated how the radiance emitted from a surface or changes with wavelength and with temperature as well. And so this is an example from 0 to 14 microns, so across the infrared spectrum. Here's just an example in the thermal infrared spectrum. These are just typical for a perfect emitter where that surface emits radiation perfectly, whereas in reality, nothing is like that. And that's where the real tool of infrared kind of comes into play. And the reason is because most Earth materials have silica or aluminum hydroxide based, and there's some distinct molecular stretching and deformation that occurs in that region, and that causes what we call absorption features. And so we can use these as a diagnostic fingerprint tool to understand what that composition of that surface is or its state. And so on the left-hand side, I'm just showing you that perfect emitter from the previous plot against what quartz actually looks like at that same temperature. And so then if we take our quartz spectrum from a laboratory spectrum, and we apply that and we take that from what that spectrum would look like if it was perfect, we then get this unitless parameter called emissivity. And so this is what we can use to do our diagnostic analyses of that surface. And again, this is the equation, those like equations at the bottom here. This can be used across different samples from solids, liquids, and gases. And what we try and do is highlight the absorption and emission features within the IR range. As I mentioned, there's a ton of applications: mineralogy, rocks, gas identification, tons of applications in remote sensing, Earth and planetary surfaces. Here's just an example of some mineral detection across the Western US, California, algal dunes, white sands. You're looking at quartz and gypsum distributions as well as calcite distributions across these sites to look at to understand alluvial processes, and we can also use these to understand, look for critical minerals as well. Obviously, there is a couple of advantages and limitations. A couple just to mention here is Thermal infrared is great because it works in the dark. You don't rely on the sun to be able to get a good signal. It's actually better if you don't have the sun. I know, right? Weird. And it's very sensitive to detecting molecular vibrations, which is great. Limitations, obviously, atmosphere is a major problem for infrared spectroscopy. There's some great working calibration, and we're making some good strides when it comes to machine learning and improving the efficiency and effectiveness of that. And also, due to requiring a higher signal to noise, the spatial resolution is typically poorer than you would get with your visible instrument. And so that's just something to consider as well. But technology is moving forward at a great rate, and we're producing new detectors that have greater sensitivities to energy in these wavelengths. So lots has been moving forward over the last few decades. And so how do I use it? I'm really interested in it because the technology typically has low power, low weight, and low cost. And so I can use that to create imaging systems, either for the ground, which is like a burst version of an instrument I built or helped build, where we took a thermal infrared camera and put a bunch of filters in front of it to slice apart that EM spectrum so we could use it as a diagnostic tool, right? And then I moved on from there to build a miniature version, which is now possible to be put onto a UAV over here, but it also can be put onto fixed-wing crewed aircraft as well. And it's been deployed over wildfires and used for some meteorology as well. So that's hopefully I've sold you on infrared spectroscopy, at least as a tool. And so I'm now going to go over how I use it for volcanic hazard modeling, specifically volcanic lava flow modeling. And so the motivation for this, as I'm sure you guys are fully aware, the interaction of lava flows and people, they don't mix very well. And there's been quite a few examples recently in the news. We've got obviously the Puna eruption in Hawaii in 2018. We had La Palma in 2021. Mount Etna is continuously erupting pretty much. And then over the last kind of 5 years, Iceland has been having those periodic lava flow eruptions, which has only recently started to really affect the communities in the region. And so my motivation here is to better, we have a good constraint on where a lava flow will go, right? It's a pretty simplistic fluid model there, right? It's going to pretty much follow drainages, but understanding where it will stop or where it may like restart, that's more of a thermodynamic question and understanding. And so what I try to tease apart is where will a lava flow propagate to, or how far will it run out, based on its regime, and what may cause it to restart and effuse again. And so I've taken these spectrometers to Hawaii to look at lava lake dynamics. So here, trying to understand, this is a small gas flare that came up on the side of the lava lake. Why does it happen here? Why not happen in somewhere else in the lava flow? What's the process that's going on here? And understanding the dynamics between that cooling lava flow and how efficiently it's emitting the energy. And then also we could do some understanding of how the plates, quote unquote, plates within the lava lake move and what's the control on that. This is a good starting point to kind of get an understanding of the relationships between temperature, emissivity, and radiation, or radiative heat loss. But really, did a lot of concentration on looking at lava flow propagation. And so on some of the previous lava flows in Hawaii, once they've stopped, you get these features called tumulus on top of them. These are topographic highs where any remnant magma or lava that hasn't been effused onto the surface, it's like squeezed out because of the weight of the overlying lava flow. And it produces these topographic highs that produce lava flows that flow, or mini lava flows that flow not very far, like a couple of meters at most. But it's a good example of how we can constrain some of the process, some of the dynamics between lava flow propagation, where it stalls and where it kind of inflates and then propagates again, right? So if you look down at this one here, when it refreshes, it inflates, and then we see a breakout here. And so it's a good example of how we can, it's a good position where we can start to develop these models. And then we take, this model and we can apply it to larger lava flows. For example, the Puna eruption that was about 13 kilometers long, and kind of validate our result from that. So I thought I'd just take a quick step back and just briefly go over some of the bounding principles of lava flow modeling. We're not reinventing the wheel; we're kind of fine tuning that wheel. There's been some great development and work done over the last 50 years by some great volcanologists that have helped us to understand behavior and what is limiting that. Mostly looking at radiative cooling, what's the transition from radiative to conductive cooling, and what that transition means for the production of a glassy crust, and then the installation of lava flows. There's been a lot of work looking at the dynamics between pahoe, so they're those ropey, smooth lava flows, so those RR lavas that we see, the clunky, and what that means, and what does that mean for high flow rate and the rapid cooling. And so what my work has been trying to do is understand what that means for our cooling regime, and understanding this relationship between propagation length, the extrusion rate, and the vent proximity. And then, finally, when we kind of boil that down a little bit more, looking at how emissivity is independent of temperature, so how efficiently our lava flow is emitting energy, and how that relates to the temperature and the state of that lava. Is it molten? Does it have a crystal cargo, or is it a full glass? And so some early laboratory experiments kind of defined how the emissivity decreases as we have a more molten or melt kind of surface or basalt, and then as that solidifies, goes through the glass transition, we see that emissivity increase. And so what does that mean for the energy that's emitted, and what does that mean for lava flow propagation? And so at that point, I then had to determine a model to base this on. There's a bunch of really good models out there. So again, there's no point in making our own model, but potentially adapting a current model that does a really nice job. And so I based a lot of my work on the FLOGO model that was developed by Andy Harris in Clermont. It's a really good model because there's a very strong constraint on the four main heat flux regimes within a lava flow, and specifically a channelized lava flow. So we have our radiative heat loss. This is where our term emissivity comes in, and that's kind of what I'm going to talk about. And that's the term I'm going to be changing a lot through the work I've done. But we also have conductive heat loss, and we also have free and forced convective heat loss if there's wind or no wind, and then we also have loss through precipitation cooling as well. And so what's the role? What is the role of emissivity when it comes to radiative heat flux and lava flow propagation? So early on, we did some calculations. We looked at how emissivity if we change the emissivity term in our calculation for radiance with wavelength, what does that mean? What does that mean? And so we took a bunch of temperatures at various emissivity values, and we see that there's this kind of similar relationship, whereas where we decrease emissivity, we also have a decrease in radiance, which is great. Again, this is for a perfect emitter. But what could this mean if we applied this simple idea to a propagation model like PyFlogo, for example? So typically it has a one component. It just has a uniform emissivity when it does this calculation for radiant heat flux. So we just did a quick back of the hand calculation and changed it. So above a certain temperature, it'll have a different emissivity value. And so what we saw is that when we decreased the emissivity at higher temperature, that the runout distance increased. So we went from if we take the one component, which is that dashed green line, against our kind of new approach, or start of our new approach, two component, we see an increase in the distance of runout of this lava flow. However, it assumes two main assumptions, right? There's only a two component solution, which we know is not true, and also we assume a uniform emissivity at all wavelengths. which was also not true, right? And so we then did some more experiments in the laboratory using a hyperspectral Michelson fast Fourier transform infrared spectrometer. At different temperatures and different states, we took basalts, we melted them to beyond their liquidus, and then we cooled them down. So going from red to blue in this plot, and we see obviously emissivity is on the y-axis here. It changes non-uniformly with wavelength or wave number as it cools. However, and this is great, and we can make a model from this. However, realistically, in the field, you can't really. It's really quite difficult to take a spectrometer and point at a lava flow. It's just unrealistic, right? So that's where we've been developing these ground-based multispectral instruments, where they don't have the spectral resolution of a hyperspectral laboratory instrument, but we can do 6-point spectrum fairly easily. We see a similar kind of trend. At higher temperatures, we see this large absorption feature, lower emissivity. As it cools, goes back through the glass transition, we see kind of that glassy spectrum, and that those emissivity values rise. So we then took that step forward, and we used the tumulus lava flows as our kind of validation on our model development, where we create a temperature dependent emissivity model. So we have on the right hand plots here, we have the data at different wavelengths for those 6 bands that we have in the instrument. We have emissivity on the y-axis and kinetic surface temperature or skim temperature on the x-axis. And we just plot that data across this lava flow for all times, and for all times temporally and spatially. There's a lot of variability at lower temperatures. Now, this is due to complex interactions with different crystal cargoes, minerals are forming potentially, or they've been brought up as xenoliths. And so there's a lot of interplay at lower temperatures. And so to kind of remove some of this noise, we did a 2 sigma variation of this, and then create our model based on that variance. And overall, we find this inverse trend between emissivity and temperature, which is kind of what we expected based on first principles. And so we could plot this and build this model. Now, there's still a slight problem where before we could actually apply it to a model like PyFlogo, we could completely change the entire model and use a 6-point spectrum. But realistically, not everyone's going to have access to this instrument, and not everyone is going to be able to determine which variables they should be using. So we create an average of this kind of model, and to be able to apply and adapt PyFlogo to ingest very quickly and very effectively, and that could be used more widely. And so we just took an average of all 6. We looked at weighting them at different wavelengths for various reasons, and I'll show you in a minute why we came up with not applying any weighting. And so from there, we then are able to apply our adapted model to the Puna eruption in 2018. And here's just a couple of thermal images of the channelized lava flow. This was around here where we have our distal very distinct channel, and then back here is this more perched Hoey channel. It's a cooler skim temperature, but it's still flowing and channelized in this instance as well. So the results, there's a few plots like this, so I'll just take a second to go over them. The y-axis is our thermoradiological property, whether that's temperature, even a physical property like channel width, heat flux, viscosity, for example. And then on the x-axis is our runout distance. The blue line is the original model without our new adaptation, and the black line is up with our adaptation, right? And what we see, we're keeping all other variables the same. We see a longer runout distance by about 7%. This is accounted for by a decrease in heat flux by about 20%. And then obviously we wanted to kind of correlate that. We correlated that with our other images from the air using the ground-based and the airborne-based imager. But we also used ground-based measurements of channel width to constrain those variables and make sure that the model was accurate. And so, we did a really nice job with that. And so just to prove to you why we decided not to weight our wavelengths, we ran a bunch of Monte Carlo simulations to determine uncertainty and significance of the model. And the top two panels is showing the number of iterations against runout distance and emissivity. With a normalized distribution of emissivity that we could use. This is for the small Touma example, and then this is for the Puna lava flow. And as you can see, our uncertainty is less than plus or minus 2% with a variability of plus or minus 3%. And it was actually worse when we tried different weightings based on our thoughts that it'd be more important to potentially account for that absorption feature at maybe 9 microns compared to something that may be happening at 12 microns. And so we came to the conclusion that just keep everything even is the best way for our model. And so to finish this section, hopefully I've convinced you a little bit at least that thermal properties vary non-uniformly downflow. We can account for that by varying temperature with emissivity and vice versa, and that using a variable emissivity model, we can better understand the radiative heat flux of these lava flows. And I'm just showing you a couple of other thermodynamic properties that are produced from the FLOGO simulation. Okay, so now I'll move on to my wildland fire work. Yes. So, as I'm sure a lot of you are aware, when you think about wildfires, you think they're destructive, and they produce, these skeletal forests. You have property losses, and lives are forever changed. People are displaced, right? Pretty dramatic events. Maybe even more so than volcanoes at this point. But fires can also be super rejuvenating, right? They can renew an ecosystem. They can make it more resilient to diseases and to invasive species. It can bring nutrients back to the soil, and it can foster new growth that's very natural and adaptive to fires in general, right? And we know this because in central Texas, where we have these grasslands and these savannas and these shrub ecosystems, typically, if we weren't here, fire would move through this landscape every 1 to 3 years. So the whole system would burn on that time scale. We've stopped that from happening. And so as a result of that and climate change, these fires are now burning longer, larger, and more frequently. We've seen big examples of this in LA. We've had massive fires in Texas, and we're seeing that happen not just in the West anymore. It's now expanding into the southeast of the United States as well. Think of Alabama, Florida, Georgia, and the Carolinas. And so understanding basics of wildland fires, how they're impacted by climate change, and understanding our key ability to predict where and when these may happen, and when they will go from something that's more rejuvenating for the landscape and go into something that's destructive, both to humans, but also to the ecosystem as a whole, right? If a fire burns too hot, it's going to kill everything. It doesn't matter if it's fire resilient or not. And so lower intensity fire is a good thing. And so understanding how we can live with fire is super important, and being able to remotely detect these fires and understand and track them from ignition can help us with mitigating not just that fire's impact on humans, but also future fire's impact on humans. And hopefully the video that I talked to can talk to you on that. And so we're interacting with fire more, as over the last 5 decades, populations have been growing. We've been moving out from the cities and into more rural areas and expanding this area, this intersection between wildland and urban, which we call the wildland urban interface, or WUI. The left is just an example for the entire US, and the right is just showing you that time for Texas itself. The I-35 corridor is probably the worst. I don't know why I'm going over that. I could just point at it. But and so our interaction with fire is becoming more prevalent, and so we're seeing more risk and more disasters because of that. I'm going to take a quick step back and just briefly go over some fire anatomy for those that aren't aware, and I'm going to talk about that with some video over the next few slides. So we have an ignition point and our wind direction. Behind, upwind, we would have a backing fire. This is typically a slow-moving fire going against wind. And then with wind, we'll have what we call our head fire, and we will also have our flanking fire as well. And from there, we can have fingers and pockets where we have some patchiness for various reasons. It could be topography, it could be because the vegetation has changed, or it could just be a naturally occurring process within the fire regime. And then we can also get spot fires. This is where the fire jumps this pretty well-defined fire perimeter and kind of breaks out from its singular regime. We can also get things like torching, where the fire progresses from the ground and into the canopy, and that can be quite dangerous. And so a lot of work I'm looking at is understanding the understanding convective convective transport of these fires, understanding the convective regimes, looking at how we transition from flaming to smoldering combustion, and if there's a way of actually going in the other direction, and also looking at this intermittent heating. So what kind of happens ahead of the flaming part of the fire? Like how does the interaction of the fire that hasn't reached that area work with the unignited fuel, and how and the role of intermittent heating has on fire progression and spread modeling. And so, this is a good example of some of the anatomy I can show you in real life. They're also showing, it's also showing some of the gases and smoke that's emitted. So across the bottom here, we have a flanking fire. The wind's going from kind of this side of the screen from right to left here. We're going to see this is going to torch. Do you see it coming into the canopy? It takes a lot of energy and a lot of heat for this to happen. It means there's a lot of what we call ground fuel and ladder fuels, which drives the fire into the canopy. And then from here, the fire can progress from one canopy, or it can progress from just a spot torch fire to a complete crown fire, and that's where they become super destructive. And so the backing portion of the fire, we back here, and the head of the fire is here. And you can see that we have slow progression along the flank. This is kind of a flanking portion of that fire. And I think in a minute, on panel there, and you can see how that progresses across the flank. And then this is kind of becoming more of a head fire as the wind kind of shifts and swirls around. And and wildfires are becoming so impactful now. They're only producing their own weather through pyrocumulus, which I'm sure Danielle's well aware of. And so what are my focus areas, right? In particular, so I developed this micro multispectral thermal imager to understand fire perimeter mapping for visual awareness and operations, looking at improving fire detection and intensity mapping, linking that to fire severity assessment. So post-fire, was the fire destructive to the whole entire ecosystem, or is it actually rejuvenating? And then linking that eventually to some air quality within like the wildland urban interface on very local scale impacts. And so how do I do this? How has my methodology been developed? Work a lot with the UT Wildflower Center. They have a large fire program, a prescribed fire program, and with them we've developed a burn box experiment where we can contain that fire at small scales for us to be able to understand fire behavior under controlled field conditions. So we can add more biomass, or we can wet the area. We can add more moisture, for example. And And we can also put a bunch of thermocouples and other instruments within that area to understand the fire regime. I use this to understand fire behavior and also validate gas retrievals. And then post-fire, we can look at rejuvenation and how temperature and energy flux have impacted the ecosystem, both from a vegetation point of view and from a soil point of view. And so, we start off with like, is this realistic, right? Does this replicate either prescribed burn or wildland fire well? And the answer is yes. To be honest, it almost does a too good a job. The burn severity that we were achieving was between 2 and 4, whereas typically for a prescribed fire, you don't really want to get above a 2. And so we're almost in that regime where we're looking really well at prescribed fire, but almost a wildfire as well. And so it's going to be really helpful for us to understand the behavior of wildfire, the introduction of biomass, and the regrowth. And so these plots here are just showing you so the treatment. So here we had no burn, we added no biomass. And when I mean biomass, we just basically got some straw and added it to the land to the box. And then when we added different number of bales of straw, we're just adding that fuel consumption. And then this is how the burn box compares to prescribed burns that we've done at the Wildfire Center in terms of like the max temperature that's been recorded. And so this is just showing from the burn boxes the temperature that we recorded at the ground level across different transects for different biomass levels. So no biomass added, and then 2 to 4 bales added. And as you can see, we've got this, we can see this degree of preheating before the fire front reaches the thermocouple. And then we see this large spike where we have the fire front, and then this gradual decrease as we go from flaming to smoldering combustion. And so we're going to use these to improve our model of understanding preheating and how the part that plays, right? And you can see that changes for different locations and for different degrees of biomass as well, right? Here, there's almost no preheating before we hit the fire, whereas in this example, there is. Here, we don't see much preheating, but we do in different examples where we have different amounts of biomass. And so we use this tool to understand those 3 areas that I'm going to quickly go through. So first point of interest for me is fire front detection and thermodynamics. So we take some, first principle thermodynamic models. Our thermal model is a well-known one within the fire community that's used operationally by fire commanders and prescribed burn bosses to understand the fire regime and how the fire might spread. And then I take observations using the infrared spectrometer, the multispectral camera. And then I scale that. So we're taking measurements from the ground. We're using thermocouples, relate that to my instrument, but then also relate that further to satellites to see if we can take that next step. And this is still work in progress, but we're getting there. And so here's just an example of one of these burn box experiments. You can see that we had 2 ignition points. It'll loop through again in a minute. There's one down here and one on the left here. And you see how that fire kind of comes together, collates, and then kind of moves through very, very quickly. What was it? There's a little bit of interference because the sides of the burn box is made of metal, and so there's some reflection there that causes some issues. But overall, it works really well, and we can see how that fire is progressing through that region. And so we can track that and whatnot. And so as a result of that, we then taken that next step further. And so instead of looking at a 5x5 meter box, I then taken drone-based, instead of on the ground, taking drone-based multispectral thermal infrared images of approximately 200 to 300 acre prescribed fire plots in the Balcony Canyonlands National Wildlife Refuge. So this has been in partnership with the Fish and Wildlife Service. They're up kind of towards Marble Falls way. And so this was the area we burnt. I'm going to show you some videos and data from in a few minutes. Mostly, savannas with patchy trees. This was what they call a slash and burn type prescription. So here they basically wanted to remove a lot of the cedar in the area, and so they cut that down, and then they burn through the landscape to remove that biomass. And you'll see what that looks like in the next slide right here. So here's just for your kind of just to give you some visuals in the visible. This is a Veneer camera. You can see where the cedar has been cut down, and then that's burning. You can see the fire front. I know it's a bit janky, but what we can see is these hot spots and these flare ups across the fire, and we can also track the fire front and also people as well. Yeah, and then we can co-locate this with thermal imagery. This is a temperature derived from those 6 bands, and so we can use the different bands to understand what's causing that heat flux that we're seeing. And so you can see where we're seeing high amounts of flaming combustion, but we can also start to pick out gases as well. Typically in these images, you'll see the gases are at a lower temperature, and that's because they're absorbing energy, and so we're seeing them at colder temperatures. And then by looking at them at certain bands, we can use that to quantify those gases. And so, I started off with small scale, then we're on a UAV, and now this is on a NASA aircraft of the same instrument over a larger wildfire or larger prescribed fire in Alabama, but also in a different condition. So this is in Alabama Geneva State Forest. It was about 1,000 acres. Yeah, 1,000 acres that they burnt over a day, and then my instrument flew over that prescribed fire multiple times over that day, over the course of that day. And so this hot fire front that you see here is actually from here, but this was quite like an hour before that fire front had really progressed. And so what we can use here is we can look at how those fire fronts progress over time and improve understanding of how the fire is moving through the different landscape. It's also really interesting because this, instead of being more of a savanna, this is a longleaf pine regime. So it's the fire moves in a slightly different manner than we would expect in grasses in central Texas. And so I've been also developing through partnership with the University of Pittsburgh and collaborators at INGV, developing hotspot tracking. So this is taking the radiance at different wavelengths, looking at band ratios and then thresholding to pick out hotspots within our normal temperature imagery here. And so this is the hotspot detection map on the right. This isn't derived directly from this image. This is the temperature image just to give you an idea of what it looks like. This is derived from that spectral data that I was kind of talking about at the very beginning. And so kind of to wrap up this a little bit, it's really that by looking at these fires at different spectral locations, we can understand the difference between smoldering and flaming combustion. That can be really important for understanding flow propagation. We can also improve our ability to do edge detection for spotting and also for torching of trees. And we can look at the temporal progression of those wildfires. And finally, we can relate the fire intensity spatially across that regime to understand how effectively either that prescription has been for the entire unit that they're trying to treat, and if they've managed to achieve their goals or not. Okay, and so next I'm just going to talk to you very quickly about gas retrievals and modeling and potentially the impact of air quality that we're definitely still working on. So this is just some laboratory work we did using the instrument to validate some of our retrieval algorithms and our gas species indices, which are shown down here. And so in the thermal infrared, there's a couple of distinctive gases we can detect because of their absorption features. So we can detect SO2, which is more of a volcanic gas than a fire-related gas, but it may be interesting. The two that are really interesting that are active in the thermal infrared is CO2 and ammonia gas as well. And so these are just some examples from the lab taking across this back body plate here of these gases and our ability to detect these in indices. So the one on the left is for ammonia, the second is for SO2, and the last one is CO2. CO2 is a challenge because there's a good amount of CO2 in the atmosphere, and so being able to differentiate between atmospheric CO2 and CO2 from our fire sources is a challenge that we're still working on, and we think there's some potential machine learning approaches that we can use to improve that. And so next, I'm just going to show you some video from the burn box. But I just want to quickly premise this by saying, so what you're looking for here is not at the box itself. Sorry, the box itself. You want to look at the atmosphere. And so we're looking for those darker colors. That's where we're seeing the gas absorption. In some places, the gases are co-located, as you kind of expect. And in some places, there's some variability depending on, and that's dependent on the temperature of which that combustion is burning and the type of combustion. So remember, we added some straw, and so that's interplaying with that, and how much moisture there is as well. And so the left is ammonia, the middle is CO2, and the right is SO2. And so, yeah, these are our kind of our first real attempt at doing this, and we're going to be refining these over the next couple of years. But so far, the results are looking really good at these high intensity experiments. And then finally, I have an undergrad student who's working with me who's looking at correlating the gas retrievals that we're collecting with the multispectral imager with PM 2.5 sensors that are around the wildland urban interface. And TCEQ have a bunch. There's a bunch of what we call purple air, community-driven ones which have open source data. And so we're using that to understand some of the impacts on PM 2.5 across the WUI. And so this is just here's where we did the burns at the Wildfire Center a couple of months ago. The wind direction was mostly from the southeast and across the days that we burnt. And then we used PM 2.5 data from the Site 1 and Site 2. We used Site 2 as our background, as our control for this instance. And then this is our kind of first order estimate of the relationship at the perturbation of PM 2.5 based on the prescribed burning. We burnt on 2 days. The first day was the 11th. We didn't see too much effect. That was likely because it probably missed this site. But on the second day, we saw 2 big perturbations. And so we're still working on correlating that with the gas emission retrievals that we did kind of on site against what that looks like and developing a transport model for that. And then finally, if I have enough time, which I might do, I'm going to briefly talk about some work my master's student has been doing looking at post-fire assessment and restoration of wildland fires, of prescribed fire, both at the Wildfire Center and at the Balcony Canyonlands National Wildlife Refuge. So Balcony Canyonlands, I showed you some early data from this burn unit. They also, a couple of days before, we also burned this burn unit to the south. And so I'll show you some results from both burn units using satellite data, as well as I'll show some temporal plots based on some of these regions of interest that I've highlighted here. So some are obviously outside the burn unit. We use that as a control, and then some are in different parts of the landscape. So some are within the dense forested part, and then some are more in the savanna grassland areas. And so produced a couple of vegetation indices, normalized difference vegetation indices, one that's used a lot, and then normalized difference moisture indices as well. And so, comparing pre and post, the bright colors will be there's been lots of regrowth. This satellite image was taken like a day after the fire, so we don't expect lots of regrowth. But what it is good to pick out is some areas where we saw kind of a large loss because of the burn. And so we see a lot in this top plot and a little bit more in this bottom plot, but that's mostly because the extra biomass that was in the upper unit based on the fact that they slashed those trees. Looking at the moisture levels, we see a high variability in that top plot again, likely because we had a higher burn severity and fire intensity. And then on the bottom two, I'm just comparing before and after with normalized burn ratio. These are the same. This is the same data. I'm just showing you in a grayscale against how we determine burn severity. And so obviously these are prescribed fire, so our burn severity is going to be low or very low. We saw our highest severities in the upper unit again because of the larger biomass, whereas where we were burning mostly grasses, we saw lower severity, and where we did see higher severity, it was where the interplay between where the fire went into the forest a little bit, but the fire didn't really move into the forest a lot. Just because of the conditions and the burn, the treatment didn't actually, the treatment characteristics didn't want the burn to actually go into the forest, so they actually achieved that goal, which is good. And so this is looking at it temporally. So NDVI, NDMI, and MBR over time for these different units. So these bottom graphs are mostly within the burn unit. As we can see, we see this large we see a decrease in some of these for a lot of these plots, but then we see a rapid restoration over a couple of months post fire. And some of this restoration is actually greater than our controlled plots, which are these two green ones at the top. So that's just shows the importance that this landscape requires fire to regenerate, and so we need to be able to do that. And it also improves resilience of this landscape. Both it removes a lot of the biomass, so that if there is a wildfire that comes through there's less material for it actually to burn, and so its effect on us and infrastructure may be less as well. And then finally, very, very quickly, I'll go over some work. We're looking at soil impacts, looking at how soil water dynamics, so that top skim is affected by fire. Essentially, we take transects pre and post fire to determine the impact on hydraulic conductivity, infiltration rate, bulk density, and water content amongst these soils. And that's important because if the soil becomes more hydrophobic, there's going to be higher runoff, less infiltration for groundwater. There's a high potential for a secondary hazard for like a landslide, for example. Maybe not in these instances, but it's interesting to understand the dynamics and how long that hydrophobicity layer lasts. And so here are a couple of our hypotheses. Essentially, we would expect water repellency to increase post-fire because we've formed that hydrophobic layer through that charring and that carbon layer that's formed on top. Across the transects on different plots, we're seeing reasonably good agreement on that. When we look at bulk density, we'd expect this to also increase because the fire breaks down the soil structure and causes compaction. We don't see really any change. I don't feel comfortable saying there's any change here, and that's likely a result of the fact that the fire severity was so low, right? It didn't really have a large impact. Also, as you see from this image, the fire is very spotty, right? So depending on where we took the sampling, depends on the degree of burning anyway. And so we're also going to correlate that with the thermal data that we've been acquiring to see if there's a relationship there. Water content, we'd expect that to decrease naturally. Obviously, we're burning something, water's going to evaporate, see a good agreement there. And then looking at hydrophobicity, we would also expect this to decrease. And it does on certain sites, but not on others. And again, this is unclear, and it's likely a result of the incomplete burning that we saw on some of these sites. And I just wanted to finish up by saying, there are some future questions that I'm interested in. So, for example, this right plot shows acres burnt in Texas from 2005 to 2021. And there's a massive amount of variability across here, right? There's no real fire season in Texas, or across Texas, right? Because we have some of these extremes in regime, from desert in the west to long pine coniferous forest in the east. And if we kind of zoom in, so I've just kind of zoomed into this bottom part here, is chaotic, right? And so understanding what are the drivers of this, I'm very interested to understand more about. And then also cascading hazards, I mentioned it briefly, right? But like if we have a fire and a drying of the landscape, will that increase our chances of debris flows in the future? And so that's also something else. With that, I'll leave you. Thank you for listening, and I'll take any questions if there are time.
Thank you, James. We have a few minutes well, 3 minutes for a couple of questions. I'll take one from a student first. Tanner, can someone pass me the mic?
Okay, thanks, James. That was really cool. My question is, you had in the plots with like the control 2 bales and 4 bales, it looked like the temperature from the plots was that it was the highest during the 2 bale scenario. Why is that versus the 4?
So yeah, that's a great question. A question we don't quite understand right now, but we think it's because there's just too much biomass, and so there's not enough oxygen. The fire triangle requires us to have fuel, ignition source, and oxygen, and we think that the bale just causes too much anoxic event, and so we're just seeing smoldering, and it's just not burning completely. So that's our current hypothesis. But yeah, still kind of teasing that apart and confirming that. But yeah, great question.
Thank you. I think Connie had a question.
Thank you so much. I was wondering, you showed these lava flows at the beginning, and they were actually quite extensive. And this is maybe not relevant for your hazard assessment, but I was wondering how well you can actually identify features of a lava flow and to what scale you can resolve them.
Yeah, sure. That's a great question. So it depends on how far away the instrument is from these features. I assume when you're talking about features, you're looking at like leve development, lava tubes, for example, right? Yeah. So I didn't show it here, but we have been able to detect underground lava tubes previously, quite effectively. But really, our ability to differentiate between those does depend on how far away we are from the source. A lot of the data we took over the Puna eruption in 2018, we were on a helicopter like 4,000 feet, I think. So, and we could look at crustal pieces moving down the lava flow we differentiate between those pretty effectively. And so our ability to detect them is dependent on how far away we are, but we can do that pretty easily. Yeah.
So for the lava flows, they sort of go a little bit further or whatever, shorter, given that you have different heat transport. But in terms of the second order features, can you actually predict something beyond that I couldn't do with just fixing whatever average viscosity or something like that?
Sure. Right. Yes, you could. You 100% could, right? Because there's no uniform solution to a lot of these models. There's not like one solution, right?
The question is, I mean, I get, right? You're measuring stuff, and that gives you sort of something that comes out as a different effect of heat flux.
Yes,
for sure, right? But then, like going beyond that, is there some predictive power in the model that includes your measurements that goes beyond looking at the average? Right? Because presumably we don't know the average properties that well.
Right. Yeah. So within the model, yes, it does recalculate viscosity or some other rheological property dependent on the heat flux regime. Yes, the answer is it does. Yeah.
Sure, but then what? Like, what do I learn that goes beyond the average?
Oh, okay. What would you learn? Well, I don't. What we tried to learn was what controls the way a lava flow will cool and how effectively it cools. So what does that necessarily mean for the development of a crust, right? And so, if it's cooling less efficiently, that crust may take longer to form than if it cools more effectively, essentially. So that's like, I think that's what you're asking.
Well, but that's sort of duh, right? I don't need the infrared observation for that, right?
Yeah.
So I know if it's not uniform, there's a peak, it's where it's smaller, larger, and I expect a different runoff. But given that you have these measurements, presumably you can infer some other things, right? That we can then use to test something else in the model.
Right. We could look at composition if that's of interest. We could definitely look at composition. We could look at xenolith composition within the this being carried by the lava. That would give us something else as well. So yeah, no, and we could also look at viscosity to a certain extent as it starts to cool and forms. We can see if there's the viscosity as well. So yeah, we can inform other things. You're right there. Thanks.
Nice work, James. I have a quick question about the fire thermodynamic model. I wonder in the model, so in the model you have the prescribed wind direction, and I wonder how the wind direction interact with the fire and the temperature field at a local scale.
Yeah, that's a great point. It's a great question. So typically fire will propagate quickest downwind. On a local scale, though, there is a bunch of eddies, and so the wind will shift pretty dramatically. As I there was a video early on, I showed the wind actually shifted direction, and so something that used to be a flank became more of a head fire, and that's a really challenging problem to understand because microclimate is a hard measurement to make in the field, especially if you have a fire moving through the area. And beyond that, a fire itself can create its own weather, depending on how hot it's burning, right? And the material that's being burnt. So it's a complex problem that it does play into the model. But the models at the moment just assume pretty much a constant wind direction with a vector per se. At a range of temperatures, a range of wind speeds. So yeah, there isn't a good account for that fluctuation in wind speed at a local level. Yeah.
Gotcha. Thank you.
All right, I'm gonna end it there since we're 5 minutes over time. Thank you so much, James, and thanks everyone for your questions and being here. Thank you. There's also going to be a student and postdoc lunch with James upstairs in the climate, well, now it's called SkyPod. Tanner's hosting that, so if you have questions about it, you can ask him. And James is in BEG, so if you have more questions for him or want to collaborate, you can get in touch with him.